The universe is a vast, ancient tapestry woven with threads of light and shadow, mystery and revelation. For millennia, humanity has gazed up at the night sky, a silent witness to cosmic ballets and colossal dramas playing out across distances so immense they defy comprehension. We have charted the paths of planets, cataloged the brilliance of stars, and even dared to glimpse the invisible architectures of galaxies. Each new discovery peels back another layer of ignorance, replacing it with understanding. Yet, sometimes, the cosmos sends us a messenger that refuses to fit our carefully constructed narratives. Sometimes, a visitor arrives from the infinite dark, carrying secrets that challenge everything we thought we knew. Tonight, we embark on a journey into one such enigma, 3I/Atlas, an interstellar comet, an unexpected guest from beyond our solar system that upon its arrival seemed ordinary. But as our instruments turned their unblinking eyes upon it, Atlas began to whisper tales of the impossible. Its brilliance shimmered with a light that shouldn't be. Its path through the void danced to a rhythm unknown to our celestial mechanics. Its very existence, a fragile cosmic anomaly, seemed to defy the fundamental rules of the universe. Join us as we delve into the quiet admissions of scientists, the untold details, and the profound questions that linger around this perplexing interstellar wanderer. This is a story for deep reflection, a cosmic lullaby that invites you to ponder the mysteries and perhaps to drift off into the gentle sleep of the cosmos. The year 2019 began like any other for the tireless sentinels of the night sky. And telescopes, those colossal eyes of humanity, scanned the velvet black, meticulously mapping celestial bodies, cataloging the familiar dance of planets and asteroids within our home system. It was a routine, yet vital, endeavor, a cosmic census keeping track of our neighborhood. Then, on the 29th of December, a flicker, a faint smudge of light, barely noticeable against the infinite star field. It was first detected by the ATLS survey, an acronym for Asteroid Terrestrial Impact Blast Alert System. Designed to spot potential impactors, it inadvertently became the harbinger of something far more extraordinary. This tiny speck, initially designated C-SEG 2019Y4, carried all the hallmarks of a common comet, a dusty snowball hurtling through space, destined to brighten as it approached the sun, its frozen heart beginning to melt and stream behind it in a luminous tail. Astronomers, with their vast databases and predictive models, could easily chart its course, calculate its speed, and forecast its behavior. Or so they thought. What appeared to be a mundane discovery would swiftly unravel into one of the most perplexing astronomical puzzles of the modern era. Imagine, if you will, living in a quiet, secluded village your entire life. You know every path, every house, every face. Your world is predictable, comfortable, and thoroughly understood. Then, one day, a stranger walks into town. Not just any stranger, but someone whose clothes are unlike anything you've ever seen, whose language is alien, and whose very presence seems to bend the rules of your familiar reality. This is what 3I/Atlas was to our solar system, a cosmic anomaly, a ghost from another galaxy, silently slipping through our familiar celestial gates. The initial observations by astronomers from institutions like the University of Hawaii and Queen's University Belfast confirmed its cometary nature, but also something far more significant, its hyperbolic orbit. Think of it like a slingshot effect. Objects bound to our sun follow elliptical paths, looping around and returning again and again. But an object on a hyperbolic trajectory is moving too fast to be captured by the sun's gravity. It enters, curves once, and then, like a stone skipping across a pond, it departs, never to return. This trajectory, combined with its velocity, was the cosmic fingerprint, the undeniable signature of an interstellar visitor. It wasn't from here. It had traveled unimaginable distances, crossing the vast emptiness between star systems, to briefly grace our cosmic neighborhood. Previous interstellar objects, like Oumuamua, had been peculiar, but they were almost universally agreed upon as asteroids, solid, rocky fragments. But 3I/Atlas was a comet, a fragile beacon of ice and dust. This was a crucial distinction. Comets, by their very nature, are relics from the earliest days of their home star system, preserving pristine material from its formation. This meant 3I/Atlas was carrying untouched samples of another star's birth, millions or even billions of years old, across the light years. It was a time capsule, a frozen message from an alien star delivered right to our cosmic doorstep. The realization sent a quiet ripple of excitement through the scientific community. Here was a chance to study extraterrestrial matter, not from our own stellar nursery, but from another. We were not just observing it from afar, we were about to witness its innermost workings, as it was warmed by our sun. This was an unprecedented opportunity, a scientific windfall that promised to rewrite our understanding of planetary formation beyond our own solar system. But as astronomers prepared their instruments for closer inspection, the excitement began to curdle into confusion, then into genuine bewilderment. Because 3I/Atlas, the unassuming stranger, was about to reveal just how truly alien it was. Its behavior was not merely unusual, it was in many respects impossible. The universe, it seemed, had sent us a paradox. As 3I/Atlas continued its inexorable journey towards the sun, astronomers eagerly awaited the inevitable display. Comets are known for their dramatic brightening. As they approach our star, the sun's warmth vaporizes the frozen gases and dust on their surface, creating a vast, luminous coma, a temporary atmosphere, and a spectacular tail stretching for millions of miles. It is this process that transforms a faint, distant speck into a dazzling celestial beacon visible even to the naked eye. Predictions were made, models were run, and expectations soared. This interstellar visitor, they theorized, would put on a show. And indeed, it did brighten. But not in the way anyone expected. Its luminosity surged, not gradually, but explosively, defying all conventional understanding of cometary behavior. Imagine a single candle suddenly flaring with the intensity of a stadium floodlight. That was the magnitude of the observed increase. By late February and early March of 2023, I/Atlas was brightening at a rate far exceeding what its estimated size and composition should allow. Astronomers track a comet's brightness using a scale where smaller numbers indicate greater luminosity. 3I/Atlas went from a dim, obscure magnitude of 19 to an astonishing magnitude of 8 in just a few weeks. This meant it had become approximately 1,600 times brighter. This wasn't merely a significant increase. It was a phenomenon that screamed for an explanation that our existing models of cometary physics simply couldn't provide. Think of a tiny campfire. You expect it to emit a certain amount of light and heat. Now imagine that tiny campfire suddenly blazing as intensely as a raging forest fire, without any additional fuel being added. The amount of light it was producing was utterly disproportionate to its apparent physical size. The core, or nucleus, of 3I/Atlas was estimated to be relatively small, perhaps a few miles across, a cosmic pebble compared to some of the solar system's giant comets, which can span tens of miles. Yet, it was outshining comets with nuclei many times its size. This impossible brightness immediately raised red flags. Comets brighten because their volatile materials, primarily water ice, carbon dioxide ice, and other frozen gases, sublimate or turn directly from solid to gas, carrying dust particles with them. This creates the glowing coma. The rate of sublimation depends on the comet's distance from the sun and the amount of volatile material exposed. With 3I/Atlas, it was as if an incredibly thin layer of ice was somehow producing a gigantic cloud of gas and dust. This was akin to a single matchstick producing the smoke of 100 cigars. One theory proposed that 3I/Atlas might possess an unusually high concentration of supervolatile materials, like carbon monoxide ice, which sublimate at extremely low temperatures, much further from the sun. If this were the case, it could explain some of the early dramatic brightening. But even this explanation strained credulity when considering the sheer scale of the light output. It would require an improbable abundance of these materials, far beyond what is typically seen in solar system comets. Another possibility was that the comet was undergoing a mini outburst, a sudden release of gas and dust from a pocket of volatile material beneath its surface. Such events are known to occur, but they are usually short-lived and localized. The sustained, exponential brightening of 3I/Atlas suggested something far more fundamental was at play. It was as if the comet itself was inherently more reflective, more active, or structurally different from any comet we had ever encountered. Scientists began to quietly, cautiously, admit that something was profoundly different about this visitor. It wasn't just its origin that was alien. Its very internal mechanics seemed to operate on a different set of rules. The impossible brightness of 3I/Atlas was the first major crack in the facade of its apparent normalcy. The initial whisper that this was no ordinary cosmic traveler. It was a puzzle wrapped in an enigma, broadcasting its secrets across millions of miles, daring us to decipher them. And as our telescopes continued to gaze, the mystery only deepened, ushering in the next, even more perplexing chapter of its short, strange life. Just as the astronomical world was buzzing with theories to explain its impossible brilliance, 3I/Atlas pulled its most dramatic and unexpected trick. It began to fade, the celestial floodlight that had been steadily intensifying, promising a naked-eye spectacle for the ages, suddenly began to dim. The surge of light faltered, sputtered, and then reversed. Between April 2nd and April 5th of 2020, its brightness plummeted. This wasn't a gentle dimming, it was a catastrophic collapse. The celestial actor, having delivered a brilliant but baffling monologue, was now exiting the stage in the middle of its performance. The fading light was a death knell. Astronomers knew immediately what it signified: fragmentation. The solid heart of the comet, its nucleus, was breaking apart. This is a known, though always spectacular, cometary phenomenon. The nucleus of a comet is not a solid monolithic rock. It is a fragile agglomeration of ice, dust, and rock, often described as a dirty snowball. It's held together by its own weak gravity and the frozen matrix of its ices. But this structure is profoundly vulnerable. Imagine taking a fragile, porous piece of glass and subjecting it to extreme stress. You heat one side while keeping the other frozen. The expanding hot side pulls against the cold, rigid side, creating immense internal tension. Cracks form, propagate, and in an instant, the entire structure shatters into a cloud of glittering shards. This is what happens to a comet. As it nears the sun, the side facing our star heats up dramatically, while the side facing deep space remains incredibly cold. This thermal stress can tear the nucleus apart from the inside out. Furthermore, the jets of gas erupting from its surface can cause it to spin faster and faster, like a figure skater pulling in their arms, until the centrifugal force overcomes the comet's own gravity, flinging it apart. For 3I/Atlas, the evidence was undeniable. Ground-based telescopes began to resolve not a single point of light at its core, but an elongated, fuzzy smudge. The comet's head was no longer a distinct, sharp concentration of light. It had become diffuse, a ghost of its former self. To confirm the diagnosis, humanity turned its most powerful eye toward the fading visitor, the Hubble Space Telescope. Orbiting high above the distorting haze of Earth's atmosphere, Hubble has the power to see with exquisite clarity, to resolve details impossible to discern from the ground. On April 20th, Hubble captured an image that confirmed every suspicion. Where there was once a single nucleus, there were now fragments. The telescope revealed a graveyard of celestial debris. The initial observations showed two distinct pieces, but just 3 days later, on April 23rd, a follow-up image was even more shocking. The comet had disintegrated into a swarm of smaller bodies. Hubble resolved at least 30 separate fragments, each one a tiny comet in its own right, enveloped in its own dusty shroud. Some of these pieces were no larger than a house, tiny embers glowing where a great fire had once been. 3I/Atlas was no more. It had become a funeral procession, a silent cascade of icy shrapnel continuing on its path through our solar system, destined to evaporate into nothingness. Yet, this fragmentation, this final act of self-destruction, deepened the mystery. Comets typically break apart when they are at their closest approach to the sun, a point known as perihelion, where the tidal forces and thermal stresses are at their absolute peak. But 3I/Atlas began its death spiral while it was still about 93 million miles from the sun, roughly the same distance as the Earth. It was still farther from the sun than Venus. For a comet to shatter so far out suggested a level of structural weakness, an inherent fragility that was almost unheard of. It was as if it were made of cosmic sugar glass, barely held together, destined to disintegrate at the slightest provocation. Why was it so fragile? Was this a characteristic of comets from other star systems? Were they built differently, from a different recipe of cosmic ingredients? Or was 3I/Atlas an anomaly even among its interstellar brethren? The fragmentation was not an answer. It was a new set of questions scrawled across the cosmos. We were no longer studying a living object. We were performing a celestial autopsy, sifting through the wreckage of a cosmic catastrophe, trying to understand how and why this emissary from the void had met such an untimely end. And from the ashes of this disintegration, a new, powerful, and ghostly theory began to rise. The death of 3Cn/Atlas was not the end of its story. In science, even an ending provides data, clues that can be pieced together to form a new understanding. The comet's impossible brightness and its profound fragility were two sides of the same enigmatic coin. They both pointed to a startling possibility that what we had witnessed was not the arrival of a solitary traveler, but merely the echo of a much grander, much older event. We weren't seeing the comet itself, but merely a fragment of its ghost. Astronomers Quanzi Ye from the University of Maryland and Zhongyi Lin of National Taiwan University began to champion a compelling theory. What if 3I/Atlas was not a complete comet? What if it was just a small piece, a shard that had broken off a much larger parent body long ago, far out in the frozen depths of interstellar space? This concept, known as hierarchical fragmentation, provided a beautifully elegant solution to the comet's perplexing behavior. Picture a colossal iceberg, a mountain of ice miles wide, drifting silently through the dark, cold waters of the Arctic. Over centuries, stresses build within it, and eventually a smaller but still significant piece calves off, breaking away to begin its own separate journey. This new, smaller iceberg, let's call it an iceberglet, is fundamentally different from its parent. It is smaller, more vulnerable, and because it was born from a fracture, it is inherently weaker. When it drifts into warmer waters, it will melt and break apart far more quickly and dramatically than the vast monolithic parent it left behind. According to this theory, 3A/Atlas was this iceberglet. Its parent was a truly massive interstellar comet, a titan perhaps tens of miles in diameter, that wandered into our solar system thousands of years ago. As this behemoth approached our sun, it didn't disintegrate completely. Instead, it shed a piece. This fragment, 3A/Atlas, continued along a nearly identical orbit, a loyal child following in its parent's unseen footsteps. This single idea suddenly explained everything. A small fragment, being porous and prefractured, would have a vastly larger surface area relative to its volume. This means that as it approached the sun, a disproportionate amount of its ice could be vaporized at once. It's like trying to light a solid log versus a pile of kindling. The kindling, with all its exposed surfaces, erupts into flame instantly. 3I/Atlas was cosmic kindling. This explains its impossible brightness. It was outgassing with an efficiency that a solid, larger body never could. Its spectacular fragility was also explained. It wasn't just a dirty snowball, it was a pre-shattered dirty snowball, held together by the barest of cosmic threads. It was born to die. Its fate sealed the moment it broke from its parent. Extrapolating its trajectory backward in time, astronomers calculated that this hypothetical parent object likely passed through our solar system sometime between 4,000 and 5,000 years ago. Imagine that, around the time the Great Pyramids were being built in Egypt, or when Stonehenge was nearing completion, a monster interstellar comet, a true giant from another star, may have silently glided through the outer reaches of our cosmic home completely unnoticed. It would have been too far away, too faint for ancient eyes to see. It left behind no record in our history, only a tiny, fragile fragment destined to make a suicidal return 5 millennia later, announcing its parent's ghostly passage. Of course, this is a theory built on inference. We have no direct proof of this parent body. It is a ghost, its existence deduced from the dying embers of its child, but it is a theory that fits the strange and contradictory evidence with remarkable precision. It transforms the story of 3I/Atlas from the tale of a single peculiar object into a chapter of a much larger unseen saga. It suggests that interstellar space is not just populated by solitary wanderers, but perhaps by families of objects, fragmented clans traveling in silent, invisible convoys across the galactic wilderness. This realization forced us to reconsider not just where 3I/Atlas came from, but what its journey truly represented. In the grand cosmic theater, orbits are the choreography of celestial bodies, dictated by the immutable laws of gravity. For the planets, asteroids, and comets of our own solar system, these paths are elegant ellipses, closed loops that bring them back, time and again, to the same points in space. They are bound to our sun, held in a gravitational embrace that has endured for 4.5 billion years. It is a predictable, reliable dance, the very clockwork of our solar system. But 3I/Atlas did not follow this familiar choreography. It danced to a different rhythm, a different law. Its path was not an ellipse, it was a hyperbola. A hyperbolic orbit is the trajectory of an object that is an unbound wanderer. It is moving too fast, carrying too much momentum to be captured by our sun's gravity. Imagine throwing a ball into the air. No matter how hard you throw it, gravity pulls it back down in a gentle arc. That arc is like an elliptical orbit. But now imagine you could throw that ball with such ferocious speed that it never fell back to Earth. It would fly upwards, curve slightly as it fought against our planet's pull, and then shoot off into the blackness of space, never to return. That is a hyperbolic path. That was the path of 3I/Atlas. Its trajectory was the ultimate proof of its interstellar origin. It was not a member of our solar family. It was a tourist, a passerby on an impossibly long journey. But its orbit was alien in more ways than one. It wasn't just its shape that was unusual, but its orientation. The planets in our solar system all orbit on a relatively flat plane, an invisible disk known as the ecliptic. Think of it as a celestial racetrack, with all the runners moving in the same direction around the central star. Most comets from our own Oort cloud also fall roughly within this plane. But 3I/Atlas arrived on a path that was wildly different. Its orbit was inclined at a steep angle of 44 degrees relative to our solar system's plane. It didn't enter through the front door. It came in through the attic window. It plunged down from above the ecliptic, swooped through our inner solar system, and was flung back out, heading up and away into the galactic north. This bizarre trajectory was another piece of the puzzle, a clue pointing to a violent and chaotic past. Objects are not typically born on such wild, inclined paths. They are forced onto them. The comet's orbit was not just a travel itinerary. It was a scar, a gravitational wound, telling a story of a cataclysmic event that had happened long ago and light years away. To understand the origin of this scar, we must journey back to the place of its birth, a stellar nursery of unimaginable chaos. Where in the vast, star-dusted expanse of the Milky Way could an object like 3I/Atlas have been born? And what cosmic force could have been powerful enough to tear it from its home and cast it out into the lonely darkness between the stars? The answer lies in the violent, turbulent youth of star systems. Our own solar system has a distant, frozen reservoir of comets called the Oort cloud, a spherical shell of trillions of icy bodies located thousands of times farther from the Sun than Pluto. These are the pristine leftovers from our system's formation, but they are, for the most part, peacefully bound to our Sun. For a comet to be ejected entirely, something far more dramatic must occur. It needs a powerful gravitational kick. Imagine a newborn star system, just a few million years old. It is not the orderly, predictable place we know today. It is a cosmic construction site, a chaotic shooting gallery. Massive, Jupiter-sized planets are still migrating, their orbits unstable, plowing through fields of smaller debris. This environment is a celestial game of billiards on a planetary scale. The giant planets are the massive billiard balls, and the comets are the tiny cue balls. When a small comet has a close encounter with a gas giant, the gravitational interaction can be explosive. The giant planet acts like a cosmic slingshot. It grabs the comet with its immense gravity, whips it around, and then flings it away with incredible force. This gravitational assist can accelerate the comet to a velocity so extreme, tens of thousands of miles per hour, that it overcomes the gravitational pull of its parent star. It is a one-way ticket to interstellar space. The comet, once a member of a stellar family, is now an orphan, a refugee cast out to wander the galaxy for millions or even billions of years. The strange, highly inclined orbit of 3I/Atlas is the telltale sign of just such a violent ejection. It suggests that it came from a system where massive planets were jostling for position, a place of profound gravitational instability. Our galaxy is filled with such systems. With over 200 billion stars in the Milky Way, astronomers estimate that countless trillions of comets and asteroids have been ejected over the eons, creating a faint, invisible web of interstellar travelers crisscrossing the void. 3I/Atlas was one such traveler. Its journey to our solar system was the final leg of an odyssey that may have lasted longer than life has existed on Earth. It was a messenger from a forgotten time and a distant, unknown place. The violence of its birth explains its journey, but it also raises a deeper question. If it was forged in a different stellar crucible, Was it made of different stuff? The chemical composition of a comet is a direct fingerprint of its home system. By analyzing the light from 3I/Atlas, we could, for the first time, read the chemical recipe of a world born around another star. The results would prove to be as strange and unexpected as everything else about this ghostly visitor. Every comet is a ghost of a world's creation. They are cosmic fossils, born in the same swirling disk of gas and dust that formed their home planets. Frozen within their icy hearts are the pristine, untouched building blocks of their native star system, a chemical blueprint from billions of years ago. By studying the comets of our own solar system, we have learned the recipe that created Earth, Jupiter, and all their siblings. But with 3I/Atlas, we were given the chance to read the ingredients list of a world born in a completely different kitchen. A kitchen orbiting an alien sun. The tool for reading this recipe is one of the most powerful in all of astronomy: spectroscopy. Spectroscopy is the art of deciphering the language of light. When sunlight passes through the cloud of gas and dust surrounding a comet, its coma, the atoms and molecules in that cloud absorb and re-emit the light. But they don't do so randomly. Each chemical element, each molecule, has a unique, unchangeable spectral fingerprint. It absorbs and emits light only at very specific wavelengths, or colors. By capturing the light from the comet and spreading it out into a rainbow, a spectrum, astronomers can see this fingerprint. It appears as a series of fine dark or bright lines, a celestial barcode that spells out, with absolute certainty, exactly what the comet is made of. Imagine holding a perfect crystal prism up to a sunbeam. It splits the pure white light into the familiar, beautiful arc of a rainbow. A spectroscope is like a supernatural version of that prism. It doesn't just show the broad colors, it reveals thousands of impossibly fine lines within that rainbow. Each line a signature, a clue. With 3I/Atlas, we were pointing this supernatural prism at the ghost of an alien world and reading its chemical soul, and the barcode we read was deeply strange. Initially, some familiar ingredients appeared. The instruments of the Neil Gehrels Swift Observatory and other powerful telescopes detected the presence of cyanogen, a simple molecule of carbon and nitrogen, and diatomic carbon, two carbon atoms bonded together. These are common in our own comets, but it was what was missing, and the ratios of what was present, that raised the alarm. Based on its extreme brightness at a great distance from the sun, astronomers had predicted that 3I/Atlas must be incredibly rich in super volatile ices, especially carbon monoxide. Carbon monoxide ice is like the dynamite of the cometary world. It turns to gas at incredibly low temperatures, driving spectacular outbursts of activity far from the sun. But the spectral data showed the exact opposite. 3I/Atlas was profoundly, shockingly depleted of carbon monoxide. Compared to the average solar system comet, it had far less of this key volatile than it should. It was like analyzing a firework and finding it contained almost no gunpowder. How could it be so brilliantly active, so explosive, while missing its primary explosive ingredient? This was a direct and baffling contradiction. The comet's behavior screamed that it was full of volatile gas, but its chemical fingerprint whispered that it was nearly empty. One theory emerged to explain this discrepancy. Perhaps 3I/Atlas wasn't poor in carbon itself, but stored it in a different form. Instead of simple carbon monoxide, it might have been rich in more complex carbon chain molecules, long, stringy compounds of carbon atoms. These molecules are less volatile but could be broken apart by the gentle sunlight in the outer solar system, releasing the diatomic carbon that astronomers observed. If true, this would be a monumental discovery. It would mean that the chemistry of its home system was fundamentally different from our own, favoring the creation of complex organic chains over simple gases. It was an alien recipe, a different way of building a world. But this alien recipe also hinted at something else, a story not of its birth, but of its impossibly long life. An object cast out into the interstellar void does not travel through a gentle emptiness. The space between stars is a vast, invisible ocean, filled with treacherous currents and a constant, unrelenting storm of high-energy radiation known as cosmic rays. These are the subatomic shrapnel of the universe, protons and atomic nuclei blasted out from supernovae and other cosmic cataclysms, accelerated to nearly the speed of light. For an interstellar traveler like 3I/Atlas, this cosmic radiation is a force of slow, patient erosion, a process of aging that unfolds over eons. Imagine a perfectly sculpted statue of ice. set out in an open field. And imagine that instead of rain, there is a constant microscopic drizzle of powerful acid. And for the first day, the statue looks unchanged. For the first year, perhaps only a slight dulling of its sharpest edges is visible. But after 1,000 years, the acid will have etched deep lines into its surface. After 1,000,000 years, it will have transformed the outer layer into a completely different substance, a hardened, discolored crust. This is what cosmic rays do to a comet. For millions or even billions of years, 3I/Atlas was weathered by this storm. This constant bombardment does two things. First, it breaks down the simple molecules on the comet's surface, like water and methane ice. This process, called irradiation, triggers chemical reactions that form a new, complex, carbon-rich crust. The comet's surface is slowly cooked, forming a dark, tough, protective layer. Second, this steady influx of energy, slowly but surely, bakes away the most volatile ices near the surface, those that require the least energy to turn into gas. The very first ingredient to be lost is carbon monoxide. The shocking lack of carbon monoxide in 3I/Atlas could therefore be interpreted as a sign of profound, almost unimaginable age. For its surface to be so depleted of this key volatile, it must have been wandering that interstellar ocean for a truly staggering amount of time. How long? The calculations are difficult, but some models suggest a journey lasting not millions but billions of years. It could be an object nearly as old as our 4.5 billion-year-old solar system, a true ancient mariner of the galaxy. It may have been ejected from its home system when life on Earth was just single-celled ooze, beginning a lonely voyage that would last for geological ages. And here, we arrive at the heart of the paradox. The ghost of a giant theory, which so perfectly explains the comet's impossible brightness and its suicidal fragility, requires it to be a fresh fragment, a piece broken off a parent body just 5,000 years ago when it passed through our solar system. The surface of such a fragment should be pristine, freshly exposed ice, rich with the very carbon monoxide it was missing. Yet, the chemical evidence, its alien recipe, points to an ancient, weathered surface, baked and processed by cosmic rays for billions of years. How can it be both? How can it be a newborn fragment and an ancient wanderer at the same time? This is the point where the quiet admissions of scientists begin. It is the moment our clean, elegant models begin to fray at the edges. The physical evidence of its behavior was in direct, screaming contradiction with the chemical evidence of its composition. It was a celestial impossibility, a walking, or rather flying, paradox. To try and untangle this knot, scientists had only one other touchstone, a single fleeting data point from another traveler who had passed this way before, the utterly bizarre and unforgettable enigma known as Oumuamua. Before the fragile mystery of 3I/Atlas graced our skies, another stranger had already passed through our solar system, a visitor so profoundly bizarre, it stretched the very definition of a celestial object. It was named Oumuamua, a Hawaiian word meaning a messenger from afar, arriving first. Discovered in 2017, it was humanity's first confirmed contact with an object from another star system, and it was nothing like we had ever imagined, where Atlas was a brilliant, disintegrating ghost of ice. Oumuamua was a dark, solid, and utterly silent specter. As it tumbled through our system, its brightness changed with a wild, predictable rhythm. It would grow 10 times brighter, then dim again, every 7 to 8 hours. This rhythmic flickering told a story of its shape. To account for such a drastic change in reflected light, Oumuamua had to be extraordinarily elongated, with some estimates suggesting it was 10 times longer than it was wide. It was a cosmic needle, a cigar-shaped or perhaps pancake-shaped object tumbling end over end as it hurtled through the void at a blistering speed of 196,000 miles per hour. No asteroid or comet in our solar system looks like that. It was an immediate and profound anomaly. But its shape was only the beginning of its strangeness. As astronomers meticulously tracked its path, they noticed something that defied the laws of celestial mechanics. Oumuamua was accelerating. After swinging around the sun, as it began its journey back out into the interstellar darkness, it was picking up speed. It was a tiny deviation, a gentle push away from the sun, but it was persistent, and it was undeniably real. This is called non-gravitational acceleration, a force other than gravity acting on the object. For a comet, the explanation is simple: outgassing. The jets of gas and dust erupting from its sun-warmed surface act like rocket thrusters, giving it a push. But Oumuamua had no tail. It had no coma. Telescopes saw nothing but a faint reddish point of light. It was accelerating without any visible means of propulsion. Imagine watching a sailboat in the middle of a perfectly calm lake, with no wind at all, suddenly begin to glide across the water, picking up speed. It's an impossible sight, a violation of the known rules. The force pushing the boat must be invisible. For Oumuamua, the cometary jets that should have been its engine were nowhere to be found. The single fact, acceleration without a tail, was so confounding that it drove some scientists to consider the most extraordinary of possibilities. Avi Loeb, an astronomer at Harvard University, famously proposed that the gentlest and most plausible explanation was that Oumuamua was not a natural object at all. Its acceleration, he argued, was consistent with that of a solar sail, a piece of advanced technology pushed by the pressure of sunlight itself. This was not a claim that it was an alien spacecraft, but the stark measure of how inexplicable the object's behavior truly was. When a natural object behaves in a way that seems to mimic artificial technology, it reveals the profound gaps in our understanding. Oumuamua was a solid, rocky, or metallic enigma that behaved like a comet. Just a few years later, 3I/Atlas arrived, an icy comet that behaved like nothing we had ever seen. The galaxy had sent us two messengers, back to back. One was a rock pretending to be a comet. The other was a comet that shattered the rules of what a comet should be. They were polar opposites, a study in cosmic contrast. Did the arrival of this second, completely different visitor help solve the puzzle? Or did it prove that the universe beyond our solar system is a far stranger and more varied place than we had ever dared to dream? Having received two distinct messages from the great unknown, the scientific community was faced with a daunting task. Translation: Oumuamua and 3I/Atlas were written in two completely different cosmic languages. One was the language of dense, dark rock and invisible forces. The other was the language of fragile ice and impossible light. These two radically different visitors tell a single cohesive story about the nature of interstellar objects, or do they paint a picture of a galaxy filled with an infinite diversity of celestial anomalies? Let us place them side by side. In one corner we have Oumuamua, small, perhaps only a few hundred meters long, dense, reddish in color, suggesting a metallic or rocky composition. It had no visible cloud of gas or dust, yet it was mysteriously accelerating, pushed by an unseen force. In the other corner, we have 3I/Atlas, a much larger, icy body, miles in diameter, surrounded by a brilliant, enormous coma. It did not accelerate mysteriously. It did something far more dramatic. It violently disintegrated under thermal stresses that should have been manageable, revealing a profound and unexpected structural weakness. For a time, these two visitors seemed to deepen the mystery, suggesting there was no typical interstellar object. But then, a new theory emerged for Oumuamua that created a stunning, unexpected bridge between the two. Astronomers Darrell Seligman and Gregory Laughlin proposed that Oumuamua's invisible engine could be explained if it wasn't made of rock at all, but of solid nitrogen ice. It was, in their words, a nitrogen iceberg. Imagine a block of frozen nitrogen, a substance that only becomes solid at temperatures below -346 degrees Fahrenheit. As this iceberg approached our sun, it wouldn't need to get very warm before the nitrogen on its surface began to sublime it, turning directly from a solid into a gas. Critically, nitrogen gas is transparent. It wouldn't carry dust with it like a water-ice comet does, so it would create a powerful, invisible thrust with no visible tail. It's like a block of dry ice, which doesn't melt into a puddle, but vanishes into an invisible cloud of carbon dioxide gas. The nitrogen iceberg theory perfectly explained Oumuamua's behavior with known physics. And here is the beautiful connection. Where would a nitrogen iceberg come from? It would most likely be a fragment, a chunk blasted off the surface of a Pluto-like exoplanet in a distant star system. This means that Oumuamua, like 3I/Atlas, was very likely a piece of a much larger parent body. Suddenly, the two messengers might be telling the same story, the story of fragmentation. It is a tale of cosmic violence, of planets and comets shattering and casting their children out into the void. Oumuamua could be a shard of a solid, distant world. 3I/Atlas could be a shard of a giant, icy comet from that same system's outer reservoir. This implies that the interstellar medium is not just filled with lonely travelers, but with the debris of entire worlds, a galactic sea of shrapnel. Our solar system may be flying through a vast, invisible graveyard of alien planetary systems. But if fragmentation is the key that unlocks the puzzle, it turns the focus back onto the central paradox of 3I/Atlas. Its behavior says it's a young fragment. Its chemistry says it's an ancient mariner. How can this be? To even begin to answer this, we must abandon our simple picture of comets as uniform dirty snowballs. We must journey deep into the heart of the comet itself and ask a more fundamental question: what secrets does its internal structure hold? For decades, the prevailing image of a comet was simple and elegant: a dirty snowball, a uniform clump of ice and rock, mixed together like concrete, hurtling through space. This model served us well, explaining the basics of their brilliant tails and ephemeral nature. But as our observations have grown more sophisticated, a new, more complex picture has emerged. A comet is not a simple snowball. It is a world in miniature with layers, geology, and a history written into its very structure. To understand the paradox of 3I/Atlas, we must abandon the simple snowball and embrace the idea of a comet with a hidden heart and a weathered cloak. Over the immense timescales of a comet's life, especially one that has wandered for billions of years, it is not inert. It changes. As it makes distant passes by its native star, or is simply baked by the relentless wash of cosmic rays, the ice on its surface doesn't just vanish. Some of it turns to gas and escapes, but some of that gas can seep down into the porous interior and refreeze, creating layers of different ice compositions. More importantly, as the ice sublimates, it leaves behind the heavier materials, the dust and rock. Over eons, this material can build up on the surface, forming a thick, dark, insulating mantle, a protective crust. Imagine a scoop of ice cream. That is the dirty snowball model. Now, imagine a ball of deep-fried ice cream. It has a cold, pristine, creamy core, but it is encased in a hot, crunchy, protective shell. This shell completely changes how the object behaves. It insulates the core, protecting it from the heat. It has a different texture, a different composition, a different story than the ice hidden within. Many comets we now believe are like this, an ancient weathered crust hiding a heart of pure primordial ice. This layered model offers a breathtakingly elegant solution to the central paradox of 3I/Atlas. Let us revisit the theory of the ghost giant. A colossal parent comet, billions of years old, wandered the galaxy. Over these eons, it developed a thick, tough crust, baked by cosmic rays. This ancient crust was depleted of its volatile gases, like carbon monoxide, and processed into complex carbon molecules, exactly matching the alien recipe we read in the comet's light. Its surface was old. Then, 5,000 years ago, this ancient mariner passed through our solar system and fragmented. A piece, our 3I/Atlas, broke away. But it was not a clean break. The fragment was a chimera, a composite of two different ages. It was composed of a large chunk of that ancient chemically old crust. But the fracture also exposed, for the first time in billions of years, the pristine, untouched, volatile-rich ice of the comet's core. Suddenly, everything clicks into place. The comet was both young and old simultaneously. The chemical signature that so puzzled astronomers came from the ancient weathered crust it wore like a cloak, but the impossible brightness, the explosive outgassing, and the suicidal fragility that all came from the fresh primordial ice from its heart. A reservoir of volatiles suddenly exposed to the warmth of our sun. It was a celestial creature with an old face and a young soul. This model of a layered composite fragment seems to resolve the contradiction. But in doing so, it shines a light on an even deeper mystery, written not in its ice, but in the very texture of its dust. Every grain of dust in a comet's tail is a microscopic messenger, a tiny particle carrying secrets of its origin. Long after the icy heart of 3I/Atlas had shattered and vanished, this cloud of dust remained, a ghostly trail of evidence for astronomers to sift through. By studying how this dust scattered the light of our sun, we could deduce its properties, its size, its shape, its very texture. And this dust, forged in the disk of another star, told a story that was, yet again, deeply paradoxical. Observations from telescopes around the world, including the TRAPPIST array in Chile, began to build a consistent picture of the dust shed by 3I/Atlas. The particles were not what we expected. They were not tiny, compact grains like microscopic sand or rock. Instead, the data suggested the dust was remarkably large and extraordinarily fluffy. They were porous aggregates, intricate structures with a vast amount of empty space, more akin to a cosmic dust bunny or a delicate snowflake than a solid speck of rock. To understand the difference, think of a grain of sand versus a dandelion seed. If you drop them both, the dense, solid grain of sand plummets directly to the ground, but the fluffy, porous dandelion seed catches the slightest breeze, floating and drifting, carried easily by the gentle pressure of the air. In space, the wind is the pressure of sunlight itself, a constant stream of photons pushing on everything it touches. The fluffy dust grains of 3I/Atlas were like celestial dandelion seeds. They were exceptionally good at catching the solar wind, which is why the comet produced such a magnificent and sprawling dust tail, a feature that was visible long after the nucleus had faded. This fluffiness is a profound clue about the comet's birthplace. Such delicate, porous structures are believed to form in the coldest, most placid regions of a young star's protoplanetary disk, far from the star, where temperatures are just a few degrees above absolute zero. Tiny ice-coated grains of dust can gently bump into each other and stick together. The process is slow, serene, and happens in an environment of extreme calm. A violent, turbulent environment would compact these grains into denser, more solid particles. The dust of 3I/Atlas, therefore, whispers a tale of a serene and gentle birth in the tranquil outer darkness of its home system. And here we find ourselves facing another stark contradiction. The comet's dust tells us it was born in a place of absolute peace, yet its wild, highly inclined orbit tells us it was ejected by an act of incredible gravitational violence, likely a close encounter with a giant migrating planet. How can both be true? How can an object be formed in a cradle of serene calm and then hurled into the void by a chaotic cataclysm? This paradox forces us to paint a more complete portrait of the alien solar system that was its home, a system that must have contained both the quiet nursery needed for its gentle birth and the violent engine required for its dramatic expulsion. From the scattered wreckage of 3I/Atlas, from its impossible light, its alien recipe, and its fluffy dust, we can begin to assemble a portrait. Like a cosmic detective arriving at the scene of a long cold case, we have only the faintest of clues. But with these clues, we can sketch the outlines of the world it left behind, a solar system lost in the star-dusted spiral arms of the Milky Way. This system, the birthplace of our visitor, must have been a place of profound and dramatic contrasts. First, it must have possessed a nursery of deep and abiding calm. The delicate, porous nature of the comet's dust tells us that its parent body was formed in an environment of extreme cold and tranquility. This would be a vast disk of gas and dust in the far outer reaches of the system, hundreds of times farther from its star than the Earth is from our sun. Here in the silent, frozen darkness, temperatures hovered just a few degrees above absolute zero. In this placid realm, tiny ice-coated dust grains could gently coalesce over millions of years, building up into the fluffy, fragile structures that we observed. This was the comet's peaceful, serene cradle. But this same solar system must have also contained an engine of incredible chaos. The comet's wild, inclined orbit and its ejection into the interstellar void could only have been caused by a gravitational interaction of immense power. This points to the existence of one or more giant planets, beasts the size of Jupiter or even larger, whose orbits were unstable. They would have carved paths of destruction through their home system, migrating inward or outward, their colossal gravity flinging any smaller bodies they encountered into new chaotic orbits or out of the system entirely. Imagine a vast, quiet, sprawling countryside, dotted with peaceful villages where life unfolds slowly and predictably. This is the outer disk where the parent comet was born. Now imagine that on the very edge of this countryside lies a superhighway for a giant, chaotic metropolis with massive, speeding trucks driving recklessly on shifting lanes. This is the realm of the giant planets. The parent comet was a resident of that quiet countryside that through some quirk of its orbit drifted too close to the cosmic highway. A close pass with a planetary truck snatched it from its peaceful life and flung it with terrifying force, not just to another city, but off the entire continent casting it out onto a lonely ocean to drift forever. This dual nature, a calm nursery and a violent engine, is not as exotic as it might sound. Our own solar system has a relatively calm outer region in the Kuiper Belt, and we know our own giant planets, Jupiter and Saturn, migrated in the distant past, creating a period of chaos known as the Late Heavy Bombardment. The home of 3I/Atlas was likely a more extreme version of this. A star, perhaps much like our Sun, with a vast cold reservoir of cometary material, and a turbulent, unsettled family of giant planets. We have a portrait of this lost home, a place of both gentle creation and catastrophic upheaval. But this entire picture is built upon one foundational assumption, that 3I/Atlas was a fragment. What if it wasn't? What if there was no ghost giant? What if the fragile visitor we witnessed was traveling alone? In the pursuit of truth, science must question its own assumptions. The ghost of a giant theory is elegant, compelling, and fits the evidence beautifully. But what if it is an illusion? What if we have been chasing a ghost, inventing a parent to explain the strange behavior of the child? We must consider the alternative. What if 3I/Atlas was not a fragment, but a complete solitary object, traveling on its own through the galaxy? If we accept this premise, the mysteries of its behavior do not vanish. They return, deeper and more profound than before. First, we must again confront its impossible brightness. If 3I/Atlas was a single solid object, just a few miles across, how did it produce such a titanic cloud of gas and dust? A solid nucleus has a limited surface area from which to sublimate ice. To generate the observed brilliance, this solitary wanderer would have to be impossibly efficient at outgassing. It couldn't be a dense, dirty snowball. It would have to be something more like a cosmic sponge, a body that was incredibly porous all the way to its core, allowing the sun's heat to penetrate deep inside and sublimate ices from a vast internal surface area. Then there is its catastrophic disintegration. The fragmentation theory explains this as the result of it being a pre-fractured, structurally weak piece. But if it was a single object, it must have survived for potentially billions of years on a punishing journey through the interstellar medium, weathering the storm of cosmic rays, only to simply fall apart from the gentle warmth of our sun at the same distance as Earth's orbit. This implies a body with almost zero structural integrity, an object barely holding itself together. Imagine a delicate meringue cookie, a structure made mostly of air, held in a fragile matrix of crystallized sugar. It is light, it is brilliant white, but it shatters into a cloud of dust at the slightest touch. The solitary wanderer hypothesis suggests that 3I/Atlas was a meringue cookie, the size of a mountain, a body of extreme and almost unbelievable fragility, that somehow survived a galactic journey intact. There is a mechanism that could explain its death without it being a fragment. As the gas jets erupted from its porous surface, they could have acted unevenly, like badly aligned thrusters. This would cause the comet to begin to spin. As it got warmer, the jets would get stronger, and it would spin faster and faster. This is a process known as rotational spin-up. For a fragile, low-density body, it would not need to spin very fast, perhaps only one rotation every few hours, before the centrifugal forces at its equator would overcome its own weak gravity, tearing it apart from the inside out. It would have spun itself to death. This hypothesis is physically plausible. It does not require an unseen parent body, but it swaps one mystery for another. It replaces the mystery of the ghost giant with the mystery of an impossible structure. Science often favors the simplest explanation, a principle known as Occam's razor. For many, the idea of a normal giant comet fragmenting is a simpler explanation than the existence of a mountain-sized cosmic meringue that just happened to visit us. But we cannot dismiss it. This deep uncertainty reminds us that we are viewing the universe through a tiny keyhole. The two messengers that have arrived so far have been utterly unalike. What other, even stranger varieties of interstellar wanderers are still out there, silently gliding through the darkness, waiting to be discovered? For the entirety of human history, our solar system seemed to be an island universe, a self-contained celestial family alone in an incomprehensibly vast ocean. The idea of visitors from other stars was the stuff of pure speculation. Then, in 2017, Oumuamua arrived. 2 years later, 3I/Atlas followed. Two radically different visitors in just over 2 years. This was not a coincidence. This was the dawn of a new era in astronomy. It was the moment we realized our island was not an island at all, but a busy port in a galactic sea. The arrival of these two confirmed interstellar objects, as different as they were, allowed astronomers to perform a calculation that was previously impossible. They could finally begin a census of these galactic wanderers. By knowing how sensitive our telescopes are, how much of the sky we are watching, and how many visitors we have found, we can estimate the total population, and the numbers that have emerged from these calculations are nothing short of consciousness-altering. Imagine you are an explorer who suspects a vast, undiscovered jungle is inhabited by a new species of animal. For centuries, all you have ever found is the occasional strange footprint in the mud. You know something is out there, but you have no idea what it is or how many there are. Then, you set up a single, modern, motion-activated camera. In the first week, it captures a clear image of a bizarre, fast-moving creature. A few days later, it captures another, completely different animal. From just those two pictures, you can now make a reasonable guess about how many animals are roaming the entire jungle. We have just turned on our cosmic motion camera, and its name is Pan-STARRS and EDLES, and soon, the Vera C. Rubin Observatory. These new sky surveys are robotic telescopes that scan the entire visible sky every single night, looking for anything that moves or changes. They are the perfect tools for catching these faint, fast-moving interstellar guests. And based on the two that we have caught so far, the estimates for the total population are staggering. At any given moment, scientists now believe there are quadrillions of interstellar objects passing through the space inside our solar system. That is a 1, followed by 15 zeros. Let that number sink in. Determinants of visitors from other stars are here, right now. The space between Earth and Mars, between Jupiter and Saturn, is not empty. It is a silent, invisible, cosmic rain of alien material. Most of these objects are small, perhaps the size of a car or a house, and dark as coal, making them impossible to see with our current technology. They are the ghosts in our celestial machine. We have only managed to spot the two brightest and most unusual specimens so far. The true population density is almost beyond comprehension. One study suggested a number as high as 100 quadrillion objects. This realization fundamentally reframes our place in the universe. Our solar system is not a sanctuary, it is a crossroads. We are constantly moving through a diffuse, invisible cloud of debris from countless other star systems. The shrapnel of alien planet formation, the ghosts of comets that died billions of years ago. We are breathing, in a cosmic sense, the dust of other suns. This constant traffic of visitors raises a profound and tantalizing question. If our home is constantly being visited by messengers from afar, could they have played a role not just in the history of our sky, but in the very history of our planet, and perhaps in the genesis of life itself? What is the origin of life? It is arguably the most profound question that science can ask. For centuries, we have assumed that life was a local phenomenon, a lucky chemical miracle that happened in the warm ponds or volcanic vents of the primordial Earth. But what if the spark was not ignited here? What if the essential ingredients, or even life itself, arrived from the stars, carried aboard a visitor like 3I/Atlas? This is the core of a theory known as panspermia, and the discovery of interstellar objects has breathed new and vigorous life into it. Panspermia is the hypothesis that life is not unique to Earth, but exists throughout the universe, and is spread from world to world by natural vehicles like comets and asteroids. We already know that the building blocks of life are not exclusively terrestrial. We have found amino acids, the fundamental components of proteins, and other complex organic molecules inside meteorites that have fallen to Earth from our own asteroid belt. Comets, being rich in both water ice and these organic compounds, are considered to be even better candidates for celestial delivery systems. Imagine a giant ancient tree, the only one of its kind, standing in the center of a vast continent. Every year, it releases millions of seed pods into the wind. These pods are tough, resilient, designed to travel for hundreds of miles. Most will land on barren rock or in salt water and never grow. But if just one of those millions of seed pods, carried by a lucky gust of wind, lands in a distant, fertile valley, it can take root and a new forest can begin. In this analogy, interstellar comets are the seed pods of the galaxy. Their icy hearts can shield delicate organic molecules, or even dormant microbes, from the lethal radiation of space for millions, even billions of years. Most will drift forever in the sterile void, But if one, just one, happens to crash into a young watery planet like the early Earth, it could deliver the seeds for a biological revolution. 3I/Atlas fits the profile of a perfect delivery vehicle. It was a water-ice comet, and its alien recipe pointed towards a chemistry rich in complex carbon chains, the very backbone of biology. While we have absolutely no evidence that it carried actual living organisms, its existence is proof that these potential seed pods are not rare. They are common. They are arriving in our solar system constantly. Now, travel back in time 4 billion years. The Earth is a young, volcanic, but water-rich world. During this era, the solar system was a much more violent place, and the planet was subjected to a constant and ferocious bombardment by comets and asteroids. If quadrillions of interstellar objects are passing through our system today, in its current quiet state, imagine how many were arriving during that chaotic youth. The sheer number of potential seed pods arriving from countless star systems across the galaxy makes the possibility of a successful delivery seem far less like a miracle and far more like a statistical inevitability. Panspermia remains a powerful, compelling, yet unproven idea. It recasts humanity's story on the most epic scale imaginable. We may not be the children of Earth, but the descendants of ancient cosmic travelers. The ghosts of comets, like 3I/Atlas, might be written into the very code of our DNA. But as we look from our deep past to our near future, these interstellar visitors represent more than just a clue to our origin. They represent a tangible frontier, an opportunity not just to see, but to someday touch the very stuff of other stars. The brief, spectacular life of 3I/Atlas in our solar system has ended. Its fragments have long since sublimated into a trail of invisible gas and dust, continuing a journey back into the void from which they came. Its story is over, but the age of interstellar discovery, the era that it helped to usher in, is just beginning. We have had 2 visitors, 2 data points. The universe has now shown us that the messengers are out there, and they are arriving. The question is no longer if another will come, but when and how many we will be ready to see. The next great leap in this quest is already taking shape on a mountaintop in Chile. It is the Vera C. Rubin Observatory, a marvel of modern engineering and humanity's next great eye on the cosmos. With a primary mirror spanning an incredible 8.4 meters and a camera containing 3,200 megapixels, the largest digital camera ever constructed, this observatory is designed for one primary purpose: to conduct a survey of the sky of unprecedented scale and speed. It will photograph the entire visible southern sky every few nights, creating a cosmic movie of the universe, cataloging anything that moves or changes with breathtaking precision. For the hunt for interstellar objects, this is a game changer. Our current telescopes are like a single security guard, armed with a pair of binoculars, occasionally scanning a vast, dark coastline for incoming ships. We have been lucky to spot the 2 that we have. The Rubin Observatory is like launching a global network of high-resolution surveillance satellites that photograph every inch of every ocean on Earth every single night, and using a supercomputer to instantly flag any vessel that wasn't there the night before. The sporadic, lucky discoveries of the past are about to become a systematic, predictable flood of new data. With this new capability, astronomers predict that our detection rate of interstellar objects will skyrocket. Instead of finding one every few years, we expect to find dozens, perhaps even hundreds, every single year. We will move from having just 2 strange specimens to study to having an entire celestial zoo. We will be able to catalog them to see if the strange properties of Oumuamua and 3I/Atlas are common, or if they were cosmic outliers. We will see cigar-shaped rocks, disintegrating comets, and perhaps other, even stranger varieties of celestial travelers we cannot yet even imagine. And with this flood of new discoveries comes an even more ambitious dream, not just to see, but to visit. An intercept mission, such as the conceptual Project Lyra, is no longer science fiction. The challenge is immense. These objects are moving at speeds of tens, even hundreds of thousands of miles per hour. We cannot chase them. The only way is to anticipate their arrival, to see them far enough out, and to launch a high-speed probe on a trajectory to meet them head-on, to fly alongside them for a few precious hours, capturing the first ever close-up images of an object from another star system. We stand on the precipice of a revolution. Soon, the trickle of information from these visitors will become a torrent. We will have a catalog of their shapes, their compositions, their origins. This new knowledge will solve many of the puzzles that 3i/Atlas left behind, but it will also bring us face to face with the most profound implication of their existence, our deep and unbreakable connection to the wider cosmos. We are told that we are stardust, that every atom in our bodies, save for the primordial hydrogen, was forged in the fiery heart of a star that lived and died long before our sun was born. It is a beautiful and humbling thought, but the story of 3i/Atlas reveals a truth that is even grander, more immediate, and more intimate. Our connection to the cosmos is not just a relic of the distant past. It is a living, breathing reality, happening all around us all the time. 3i/Atlas was never just a comet. It was a paradox, a whisper of a ghost giant, a chemical messenger from a lost home. It was the second verse in a song that began with Oumuamua, a song that tells of a galaxy not of isolated islands, but of a vast, interconnected ecosystem. It confirmed that the space between the stars is not empty, but is instead a thoroughfare, a cosmic highway teeming with unseen travelers. Imagine the galaxy not as a collection of separate stars, but as a single sprawling organism, celestial brain with 200 billion stellar neurons. For this brain to function, for it to be a cohesive whole, information must be exchanged. Interstellar objects are the neurotransmitters of this cosmic mind. They are the physical vessels that carry chemical and physical information from one star system to another, ensuring that no part of the galaxy truly evolves in isolation. The dust from a system that died a billion years ago becomes a building block for planets in a system just being born today. The quadrillions of visitors passing silently through our solar system at this very moment are the living embodiment of this connection. They are the threads of a great cosmic web, a physical link between our home and every other star you can see in the night sky, and the billions more that you cannot. When you gaze up at the velvet darkness, you are not merely looking at distant, disconnected points of light. You are looking at the birthplaces of the silent travelers who are, at this very second, gliding unseen past the orbit of Mars or sweeping out beyond the rings of Saturn. The perceived barrier between here and out there is a gentle illusion. The mysteries of 3i/Atlas, of its impossible brightness and its paradoxical nature, may never be fully solved. But in the end, its most important message was not written in the language of physics or chemistry. It was a message of belonging, the faint fading light of a disintegrating comet, a fragile ghost from an unknown star, was a quiet reminder of our own cosmic heritage. A reminder that our planet, our sun, and our very bodies are woven from the same fabric as the most distant and ancient of stars. We are not just looking at the universe, we are a part of it. And now, as our long journey into this mystery comes to a close, we can rest, knowing we are home, adrift together in a silent, star-dusted sea.